Okay, happy Wednesday, everyone. Welcome to class. So, our learning objectives for today, the one thing we didn't get to last time was calculating theoretical density for these crystals. So we're going to start with that. Then we're going to use the cation-anion ratio, so the ratio of the size of these different things. Amazingly enough, you can actually take that ratio and it gives you a pretty good estimate of the crystal structure. I'll show you how to do that. We're going to talk about some basic structures that you should be aware of and be able to draw. Things like sodium chloride, cesium chloride, rutile, perovskite, zinc blend. We'll describe what those are. Then we'll introduce, you won't expect to draw these, but I'm going to introduce some of the ideas of how clays and silicates work. We'll talk about carbon. And hopefully by the end of today, we'll have started the different crystal systems that exist and how to draw planes in these things. That's on the docket for today. So the last thing I want to cover from last time that I didn't quite get to, we said the FCC, face-centered cubic, has a packing fraction which is the highest you can get, 74%. That's if they're all the same size, right? If you now start introducing small ones and big ones, you can get a little bit higher. If you do small, big, and really small, you can get even higher. You can get up to like 90% with a trimodal distribution. But if it's all the same size, 74%. And then we said hexagonal close packed is the exact same. It can also reach the same amount, which is surprising. So this is the hexagonal unit cell like many people would want to draw it. This is not the smallest unit cell, though, right? We said the smallest unit cell is what we call the primitive unit cell, and the smallest one that you could tile without flipping it or anything like that would be this guy right here. That on top of that with these lines coming down. And if you look at that, on the bottom there's atoms at each one of these corners, but the layer in the middle has this atom right here, and it is located directly above, and they tried to show that with this dotted line. It's directly in the center of this triangle. Okay? In other words, it's sitting at the interstitial site between those, and then rotated or translated up a little bit along the C-axis. The C or the Z-axis. They typically call it the C. Okay? So what would be the coordination number in in hexagonal close packed HCP? Let's pick an atom and let's count it. Let's start with this guy right there. What would be the coordination number for that? The same number of atoms that are equally close. Well, there's the 6 that are around it, right, in what's called the basal plane. This whole thing up here, or at the bottom, is called the basal plane. Okay? So there's 6. But because these things are spheres and they're all the same size, and it's sitting on the interstitial of these 3, it's equally close to those ones as well, right? In other words, if I was looking straight down on this, it would look like this. We'd have spheres being packed. There's our top layer. That's the basal plane, right? I kind of jacked that up. It's not really better, but... right? There's our 6 atoms. This one in the dead center, it's sitting on top of, let's draw it in a different color, an atom there, there, and there. Can you guys see that? And then just above it, it's got the same 3 just like that. So if you add it up, it's equally distant to all those. It's touching all of those. So it's got 6 on the 2-dimensional flat plane around it, and then it's got 3 below, 3 above. It also has a coordination number of 12, just like face-centered cubic had, which is why, not surprisingly, since they have the same coordination number and they're both stacks of atoms in the same sort of way, they both can achieve the same stacking of 74%. Are there any questions about this? I have a cool demo that I forgot to bring. Contemplating whether to send Danny for it. Yeah, Danny, you want to go grab it for me? By the end of class, we'll show you a good example of this. Look at the tennis balls. There's a box full of tennis balls. Okay. So we'll come back to that and show you how on earth something that seems very counterintuitive, like a hexagonal unit cell and a cubic one being the same, we'll show you how they're actually not that different, how you can get to it. So let's keep going. Let's start then with theoretical density. When you calculate density, you've been doing this since high school, it's mass divided by volume. Here we're going to do it the exact same way. The only catch is that we have to take into account the molecular mass, right? The molecular weight of different atoms, right? Not all atoms weigh the same amount. So the way that we do this that's sort of the most convenient way to do it, is we say that rho, the density, is equal to Z, where Z is the number of atoms or molecules per unit cell. M sub W, that's our molecular weight. That's on an either atom basis or on a molecule basis, right? So you could do this two ways. You could say that there are two formula units, right? Z could be written as formula units of something like Al2O3. And if you did that, then your molecular weight needs to be the entire formula of alumina, right? So 26.97 or whatever it is, grams per mole times 2 plus 3 times 15.999 grams per mole, right? That would be our molecular weight, okay? You could do this exact same thing on a per atom basis if you wanted, right? Z would be 2 aluminums, and Z would be 3 oxygens, right? And then you do the molecular weight of aluminum. It doesn't matter, but this is a common mistake that people will get wrong. Okay? It's just correctly adding up the number of atoms in the unit cell. So, for example, if it was FCC, if we were figuring out FCC or BCC, let's do BCC for instance, it's right there. What would Z be if we were trying to calculate, let's say this is iron, BCC iron, that's ferrite. What would Z be for BCC iron? How many atoms are there per unit cell? 2, right? So you'd be 2 times the molecular weight of iron in this case, and then you need to divide it by the volume of the unit cell. If it's a cube, it's really easy. The volume of the cube is simple. It's whatever this lattice parameter is, A cubed. Okay? Straightforward enough. What else do we have to add? Well, the mass is in a per mole base, right? When like aluminum is 26 point whatever, 9 grams per mole. So you need to account for those moles by putting Avogadro's number in the bottom of this expression, like so. Right there. It's got to be the volume of the unit cell multiplied by Avogadro's number. Otherwise, you won't get the right answer. Okay? That turns it into a per atom basis as opposed to a mole of substance basis. Are there any questions on theoretical density? Yeah, Ryan?
BCC, where did you get the 2 atoms from?
Okay. Where did we know? How do we know it's 2? So we did this last class, and basically we said, all right, let's count up how many atoms are actually inside this cube. And we said there's 8 that are kind of partly inside. They're located on a corner. So 8, and they're actually 1/8 of the way inside. And the book has a nice diagram to show this. And then there's 1 completely inside. So 8 times 1/8 plus 1 gives us the 2. All right, let's ask you this one. What about hexagonal close packed? This one's trickier. How many atoms are there per unit cell? This red area is the unit cell, the primitive unit cell. How many atoms are present there? There's 1 that's completely inside, and then you've got these things, but that's not 1/8 of the way in, right? If you looked down on that, let me redraw this. You've got atoms located like this, okay? And the unit cell was this red area. So what fraction of the atom is actually inside the primitive unit cell? What do you got?
1/6.
Well, it depends. This one's 1/6, right? That pie slice, there's 1/6, 2/6, 3/6. That's half, 4, 5, 6. But this one's not. This one's got 1, 2 of those, right? So this is 1/3 of the way in, at least as it's projected here. This is 1/6. But remember, this has to include both above and below it as well. So this 1/3 is actually 1/6. You have to divide it by 2, right? Because half of it's actually in the unit cell. Let's assume the unit cell is coming out. We only get to count the positive half. The part that's going into the board, we don't get to count. So it's 1/3 divided by 2 is 1/6. This then would be 1/6 divided by 2 is 1/12. So you'd have to add these up. You have 1, 2 of those plus the 2 above. So you've got 2 1/12 plus 2 1/6 plus the 1 in the dead center. If you add it up, it's 2. There's 2 atoms per unit cell in HCP, right? The vast majority of things I'm going to ask you to do in this class are cubic. HCP is the only other one that we really deal with. And then tetragonal, but that's not much harder than cubic. We'll show you in a minute, okay? Any questions on counting these things? No? Keep going. Thank you, Danny. So let's do a quick example. How on earth, I've been saying that cubic and hexagonal are kind of related. So what I've got here is a bunch of tennis balls, right? They're all the same size, and I've put them together in a hexagonal arrangement. Can you guys see that? It's a hexagonal arrangement on the bottom layer. Now, when you go to put your next layer in there, you've got options. If you look at this, see how there's this one is a triangle pointing up spot right there? Can you guys see that in the back? It looks like a triangle, but it's pointing up. All right, document camera. We're going to use it. Think it's turning on? Maybe. This will be a first time using a strange new tool. Can I change the... Oh, yeah, it's got to focus. Okay. You guys see a bunch of tennis balls here, okay? Okay. So when you're looking at this, I'm all turned around, but you've got options. You've got... That is a triangle pointing up, and this one right here is a triangle pointing down. See that? I can choose to put the tennis ball on the up spot or the down spot, but I can't do both because they would overlap. You guys see that? So we're going to name these things layers. Let's call the bottom layer the A layer, okay? We're going to call it A. And then if I choose to put it on a triangle, that is up, right? Does that look up to you as well? Yeah. This spot right here? Oh gosh, my hand is doing things that make my brain not want to keep going. All right, I put that on a triangle up spot. Let's call that the B site, okay? So I could fill these things on the B site. For simplicity, I'm going to put a, let's actually do the triangle down. See this spot right here? How that's a triangle down spot? Am I confusing more people than helping? I'm going to stack on the B site, okay? Okay. Wait for it. It's actually helpful. Okay. Okay. You guys see that? How I've just created like another layer of atoms, but I didn't stack it directly on top of the site before like this. I moved it over a little bit, okay? Now we have an option. If you want hexagonal close packed, you go back to where it was originally, okay? What's in the frame of view? Like the one where it was originally was right there. Can you see the one below it? That was where one was before. If you do that, you will get hexagonal close packed. You just keep on switching layers like this. Not very interesting. What's trickier to see and pretty cool is that this can also give us cubic. If I, instead of going to that spot, if I go to the other spot that we didn't use before, it's cubic. Now you're like, that's not a cube, Dr. Sparks. It is, but it helps to see it if I zoom out just a little bit. You see the green balls? The green balls are the corners of the cube. I keep moving it the wrong way. Do you guys see that? Do you see the corners of the cube? And you see that there are balls on the faces. We have a face-centered... Oh, this is so hard. We have a face-centered cubic arrangement. I don't know if this is actually helping. But you are welcome to come make your own. There's like a cube there if you look at the green balls. So it has to do with the stacking of these layers. If you just alternate A, B, hexagonal close packed. If you do A, B, C, you end up with this funky way of getting a cube, which was not obvious at first glance. Okay? Did I confuse more people than I helped? Is that clear-ish? Can I answer any questions? Okay, let's keep going. So let's do an example. Let's calculate the theoretical density of something, right? So let's do face-centered cubic copper. What should the density be? Well, last class we gave you the lattice parameter of copper, right? And we said it was right here. The lattice parameter is 3.601. So let's calculate its theoretical density, and then we'll Google what the density of copper is and see if we're even ballpark close, okay? So 3.601. Okay. So in face-centered cubic copper, FCC copper, we're going to say that rho is equal to, there's 4 atoms per unit cell in face-centered cubic, 1 on the corners, 3 on the faces, so there's 4 total, times the molecular weight of copper, which is 55 something. What is it? What's copper? Copper is 63.55. 63.55. That's grams per mole. Okay? So 4 atoms times their weight. We don't have to do volume here on the numerator. Volume is in the denominator. It's 3.601 angstroms. And we need to cube that. Right? And then the last thing we need is we need molecular, the number of atoms per mole, which is Avogadro's number. So let's grab this thing and give ourselves room for, oh, jeez. Okay. So let's multiply this by Avogadro's number, 6.023 times 10 to the 23rd on a per mole basis. Okay? Somebody punch that in. What will the units be if we punch this in? What cancels? The per moles cancel. So we're going to end up with grams per angstrom cubed. Is that a useful measure of density? Not particularly. It's going to be some tiny, tiny number. Tiny, tiny number. But much more common is kilograms per meter cubed or grams per centimeter cubed. That's the most common units of density. Yeah, Ryan? Ryan?
Why did you cube the equation?
Why? Good question. Why is 3.601 cubed? We need to take, density is the mass of something per volume, and it's a cube. This is the edge length of a cube, so we cube it to get the volume of the cube. So let's do this in grams per centimeter cubed. That's a much more reasonable density. So we're going to get rid of this stuff. And we're going to do 3.601. To turn it into meters would be 10 times 10 to the negative 10. 10 times 10 to the negative 8, we'll put it in centimeters. So e to the negative 8, that gives us centimeters. Cube that. So punch that in for me. What do you get? Let's see how that compares with the real density. Okay, so the actual measured density near room temperature is about 9 grams per centimeter cubed. When I punch it in, I get 9.03, right? Or in other words, copper, if you just account for the unit cell, it should be a little bit more dense than the copper that you can buy at Home Depot. So what gives? Why is it not a 100% match? This equals 9.03 grams per centimeter cubed, cc, versus 8.96 grams per cc experimental. What gives? What do you think's happening? Is it Andrew?
Yeah. Is it because the number of copper atoms in the unit cell is always slightly changing because they're vibrating?
Ah, that's a good guess. I think that's partly the answer. What would heat do? Heat makes things expand and contract. Or in other words, this 3.601 angstroms, maybe that's not exactly at room temperature. And this was taken at room temperature, it said. So maybe we need to change this a little bit. Maybe. What do you think?
There could be like missing things from
Yep.
all the things.
Yeah, I mean, this is the lattice, right? We've shown you this thing. Like, can that exist? It can. You can have missing atoms. These are called vacancies. We will talk way more about them next 2 chapters from now, right? So basically, you can have missing atoms, and that will bring your density down a little bit. So maybe that's what's happening, right? It would like to be 9.033 if it was totally occupied, but maybe it's missing some. That's probably one of the biggest factors on why the density doesn't match. Okay? Any questions on how to do theoretical density? Yeah. Depends on what you're doing. Yeah. Some applications you would need the experimental maybe. You can actually model how they change. So it depends on the application. It's kind of the short answer. It certainly gets you pretty close. Okay? Yeah.
So is it the missing atoms or is it some other process or is it like crystal defect?
So a crystal defect is a missing atom, but there's other types of defects. There's things called, well, grain boundaries. That's a defect, right? And that is an imperfect stacking, right? I could stack students in this middle section more efficiently than maybe these boundaries because the seats fit weird or something like that. So that's going to lower your density. There's something called dislocations, which we haven't talked about, but we will soon. There's other things that can go wrong. But generally, you see pretty good agreement. Okay? So we could do this for, again, how would we do this problem differently if instead of a single simple metal like FCC, what if it was a ceramic structure? How would we have to modify it? Ceramic structures, you're typically talking about a formula unit, like alumina, right? So again, then instead of counting individual atoms, it's much more common to say how many formula units exist inside the unit cell. And on your homework that is assigned today that you can start for this coming week, you'll have an example of doing that. It's some compound like strontium titanate. And you could count up the individual atoms if you want, but I wouldn't because there's like a gazillion oxygens in there. Instead, pick the ones that are easy to count, like the strontium, and then you know what the formula unit is. It's Sr2Ti4O8. So if you count the number of strontiums, you know how many formula units there are. You don't have to count up all the individual atoms. Okay? I think we'll have a chance to show an example of this. Let's keep moving. Okay, speaking of ceramics, ceramics make our structures more complicated. The metals were easy. FCC, simple cubic, BCC, HCP. There's really only like the 4 for simple metals. But once you start introducing ceramics, it's harder because now you've got 2 different sized ions. You've got your cation, which is small, and your anion, which is large. Like imagine how many different structures we could come up with this if instead of them all being tennis balls the same size, what if I had marbles too? There's all sorts of different ways that I could put those together. Maybe you could take the regular stacking just like before, but you've got like a marble in between filling up the gap between them. That's a new type of structure, right? So that's the sort of stuff that becomes possible with ceramics. Something that helps us figure out what structure it will be is taking the ratio of the size, okay? So how does this work? RC is the radius of the cation. RA is the radius of the anion. And if you take RC and you divide it by RA, it should be a number less than 1 because cations, because they've lost electrons, have shrunk in size. And anions, because they've picked up electrons, typically get bigger. So oxygen, even though it's not that far down on the periodic table, oxygen's like way up here, it's actually a ginormous ion. It's 1.35 angstroms as opposed to iron, which is like 0.5. It's like 3 times almost bigger than iron, okay? So cations tend to be small, anions tend to be big. Because of that, you end up with this scenario where if this is your cation and this is your anion, which is bigger than it, if it's going to surround it, it's going to be stable if these ions are touching. So here it's like the perfect size to be touching. Here it's still stable, but here the cation is too small and so it can't be touching the ions around it, the anions. That's unstable, okay? That is less likely to form from a free energy, a Gibbs free energy standpoint. This one on the right over here is unstable because it's not touching, because it's too small. So how could you fix this arrangement and let it be touching? Change the number of anions that are around it. Instead of having 4, what if you did this? If you do 3 instead of 4, then a smaller cation can still be touching the larger anions. That makes sense? In other words, the ratio of the size will tell you how many anions are surrounding your cation. So we have this handy table which says the coordination number of your cation will be one of these numbers if the RC to RA ratio lies in one of these ranges. Okay? Which is pretty slick. So let's do an example. Like magnesium oxide. Let's do sodium chloride. We're going to do it in a minute anyways. Sodium chloride is rock salt. So we pull up sodium and we say, what's the charge of sodium? It's only ever +1. It only ever wants to get rid of an electron. Okay? So the size that it takes is over here, and the size depends on the coordination number, okay? But it ranges basically between 1 and all the way up to 1.4. That's the typical size. which is kind of weird. We think of things as being like a fixed size. What this means is like the size of atoms depends on its environment. They can squish a little bit. And if you give it a really big box, like 12 nearest neighbors, it's surrounded by 12 neighbors, it's going to be the biggest version that sodium can be. But if you squeeze it down where it's surrounded by 4 nearest neighbors, it's going to be the smallest version that sodium can be. Does this make sense? Think of like the Death Star in Star Wars, right? The Death Star is massive, so how many TIE fighters could go around it? Tons, right? Yeah, question? Why not Star Wars references?
I'm fine with it. I just couldn't tell if you did it or if it was like the TA.
Those were our doing. We, in the past, have done whole exams on it. You think I'm joking. Okay, so let's compare that to chlorine. Chlorine, if it's -1, which is its most common state, it only exists when it has 6 neighbors. That's like the only way that you can find chlorine. And its size is 1.8. So let's do an example here. Let's assume that sodium is 6 coordinate, because that's what it is in this case. It's about 1. 1 divided by 1.8. 1 divided by 1.8 is what? What's the answer there? 1 divided by 1.8 is 0.55, okay? So 0.55, what coordination number should it have? 0.55 puts us right here, meaning it should be 6 coordinate. The coordination number of our cation should be 6, okay? So this is a pretty handy tool. There's exceptions, just like everything. There's exceptions to this general rule, but this helps. Now let me ask you, what does it look like? What's the shape of the object that's surrounded by 6 nearest neighbors? What do we call that shape? It looks like 2 pyramids, like back to back. Like you've got like the base of a pyramid pointing up to something, and you've got it also pointing down to something. What's the name of this? Nope. Not tetrahedral, but you're getting closer. Octahedral. Why do they call it octahedral? Octa sounds like 8, and yet this is 6. What did they do wrong? There's 8 faces. Yeah, there's 8 faces to that, right? The pyramid has 4 faces, and there's 2 of them. So this is called octahedral. Octahedral. This one would be called tetrahedral if it's 4. If it's 3, we call it trigonal planar. I'm just going to type these because you can't read that. Okay? Over here, this would be linear. This would be trigonal planar. This would be tetrahedral. This would be octahedral. What would 8 be? It's surrounded by 8 atoms. We've seen this before. Like body-centered cubic has the one in the center and it's surrounded by 8 around it, equal distance. It's cubic. That's a cubic arrangement. And then the last one would be dodecahedral, which is harder to visualize, but the internet exists. Dodecahedron. A dodecahedron has, it is, it looks like, these pictures are worthless. Kind of like this one. Like that one. That's dodecahedral. Okay? 12, it's surrounded by 12 things. Okay, does this make sense? That basically the size ratio of your anion and cation will roughly tell you what the coordination number should be for the cation. If it's a really big difference, it's going to be linear. If it's pretty close to the same size, it'll be dodecahedral. Okay? And anywhere in between. Okay, the first type of ceramic structure that we should know is rock salt, which we just calculated should have a coordination number of 6. So let's see if it does. You've got your sodium ion small in black, and then you've got your chlorines. So let's pick like, I don't know, say this guy. Is it surrounded by 6 chlorines? Well, it's got 4 in the same plane as it, to the left, right, front, and back. It's got 1 above. And if we drew another unit cell underneath this, there'd be another one directly below it. So it has 6. Any one of these would have 6. It helps if you draw the rest of the unit cells maybe to see it, but they all have 6. Now in this case, the cation and the anion both have the same coordination number. Or in other words, if we take the chlorine and you look at how many black atoms surround it, it's got 1, 2, 3, 4, 5, 6. It's got that octahedral coordination. They both have a coordination number of 6 because the ratio of sodium to chlorine atoms is 1 to 1. If they had a different ratio, then they wouldn't have the same coordination number. And we'll show you an example of that. Abigail? Question? The way that we found the coordination number for the cation was by looking up their sizes, and we found that the size of the cation was 1 angstroms. The size of the anion, chlorine, was 1.8. We divided them. It was 0.55. So then we used our handy chart here, and we said, 0.55 lives right here in this range. Therefore, it must be surrounded by 6. Our cation must be surrounded by 6. The table suggested that, and there's exceptions to the rule, but it's a pretty good table. It works a lot of the time. Okay? Now, this structure looks familiar. What structure does it look like that we've already seen in metals? Take a look at the black atoms. They're located at the corners, and you've also got them at the faces, the front face, the right face. This looks like face-centered cubic, except we've put other atoms in the interstitials. So, for example, we stuffed one here. Okay? And then if you look at these ones, these are also forming a face-centered cubic lattice. Let's draw another unit cell over. If we draw another unit cell over, it would have these the anions in red. I'll show those. They also form a face, right? Or in other words, you could draw another unit cell like that, and it would look like a face-centered anion. You guys see that? In other words, these are two interpenetrating face-centered cubic lattices. Okay? That's why it's useful to start out with metals, because a lot of the more complicated structures are really just variations of what we've already seen. In this case, it's two FCC lattices that are offset by half of the lattice parameter. The black is an FCC, and the gray is also an FCC. They're just offset by half of a unit cell. Make sense? Does it not make sense? Can I explain something better? Should we keep going? Let's keep going. And again, if you want to see it again, if you didn't see that before, this could be a unit cell just as easily. Right? They could have just as easily chosen to draw the unit cell starting on the cation as opposed to the anion. It'd be the same thing. You could still tile it to fill all space. It's just a choice they made. Okay? Okay, the next structure you should learn about is cesium chloride. Cesium chloride is this one right here. What does it look like that we saw already? It looks like body-centered cubic. Why does it get its own name? Why don't we just call this body-centered cubic? Yeah, these are two different atoms. Body-centered cubic, by definition, these have to be the same atom at the corners as the center. That's not what we have here. We have two different atoms. You've got cesium and chlorine. Okay? Now, if you did the math on this, first off, cesium, what is the coordination number of our cation? 8. So, do you think it's bigger than or smaller than sodium, using our table here? Do you expect that cesium is bigger than or smaller than sodium? Its coordination number is 8, meaning the ratio was larger. The ratio of RC divided by RA was a larger number. So is cesium, our cation, larger or smaller? Yeah, if you're taking RC, dividing it by RA, let's assume that A hasn't changed very much. RA hasn't changed very much. In order to get a larger number, you need to have a larger cation. And sure enough, cesium is a whole lot bigger than sodium. Okay? Which is why it adopts a different structure. This making sense? This is actually kind of slick. It explains why on earth, I started out this chapter saying there's 10,000 different structures. And once you understand some of these basic rules, and it's simple stuff like charge and size, that dictates why on earth different compounds crystallize in all this variety of different structures. And it's all about just minimizing your energy. Okay? You could think of this, just like before, as in terms of things we've already seen. It's not BCC, but it is two interpenetrating simple cubic lattices, right? You could take simple cubic lattices. This time it's offset by 1/2 a unit cell, 1/2 a unit cell, and 1/2 a unit cell. So it's along the body diagonal that it's shifted 1/2 a unit cell. But it's still two interpenetrating, but this time simple cubic lattices, okay? The next structure you should know is called zinc blende. This is the one that I brought to class the other day, zinc blende, also known as the diamond structure. The difference between this and diamond is that if this were diamond, the yellow and the gray would be the same thing. In this case, they're not, so it has its own name. It's called zinc blende, because that's the name of the mineral for zinc sulfide. Zinc sulfide, when you dig it out of the ground, somebody named it zinc blende. It wasn't me, don't blame me. But it forms in this structure. And if you did the math on this one, the RC over RA ratio, RC over RA, zinc is even smaller than sodium, smaller than cesium, and so this ratio is even smaller, and you end up in a tetrahedral range. It's somewhere between 0.25 and 0.414. So you end up with a tetrahedral, or a fourfold coordination. Do you see the fourfold coordination here? Take a look at the gray atom. It's surrounded by 4 yellow atoms. Let's show you this one. It's a little easier to see if I show you a couple unit cells. So let's pull up zinc blende and make a couple unit cells. Okay? Is yellow also surrounded by 4 grays, is the next question, right? So if you look at it, gray is certainly surrounded by 4 yellow. That guy's got 1, 2, 3, 4. Well, now pick a yellow. Yeah, how about this one on the side of the unit cell? That one over there. That's hard to see. You see that one? It's surrounded by 4 gray. Okay? So in all the cases I've shown you so far, the coordination number of the cation is equal to the coordination number of the anion. It doesn't have to be that way. It is in these cases because all of these compounds I've shown you are 1-to-1 ratios. 1 part sodium, 1 part chlorine, sodium chloride, cesium chloride, zinc sulfide. They're all 1-to-1. If it's a 1-to-2 ratio or a 1-to-3 ratio or something, then the coordination number cannot be the same. And I'll show you an example of that. Okay? And again, this one can be thought of as 2 interpenetrating FCC lattices, but this time shifted by a quarter. Here's how we can see that. Let's take a look at, okay, this one right here. So, let me rotate it so we can see it easily. How about this one? Okay, we're going to start here. And we want to get rid of B and add a C. Let me do that real quick. Get rid of a B, add a C. Okay. So let's outline the new lattice corner will be this guy. He's at the corner of the unit cell. So you can see that along that face, how those gray atoms line up, that's a face, the front face. So that would be a corner, a corner, a corner, a corner, and a face. So it's also an FCC lattice. But instead of being shifted half of the unit cell like it was in sodium chloride structure, it's shifted by a quarter, and a quarter. Does this make sense? If we drew these things, I don't know what's going to happen here. If we do space filling, the way that they touch one another is along the body diagonal. These two that are lined up right here, they touch along that body diagonal. Okay? So if you wanted to figure out the lattice parameter to ionic size ratio, what would it be? Let's do that one. If I gave you the radii of these things, and I asked you to tell me the lattice parameter, what would you do? Well, you'd say they're touching along that bond right there, right? That's where they're touching, is where the bond exists. So what's the size of zinc and sulfur? Let's pull those up. Okay, we'll start with zinc. Zinc 2+ in a 4-fold coordination is 0.6 angstroms. So the radius of zinc 2+ is equal to 0.6 angstroms. It's small. Meanwhile, sulfur is going to be 1.4 or something. In a 4-fold coordination, it only shows 6, but it's 1.8. So let's use that value and see how close we get. the radius of sorry, not oxygen, but sulfur, 2 minus, is equal to 1.8, okay, roughly. So how would we figure out the lattice parameter from this? Well, what do we know? We know that they touch along the body diagonal, but they don't go all the way across. With body-centered cubic, it was easy. We just took 4 radii, went all the way across. Here, they only go a quarter of the way across. In other words, this distance from here to here, we know what that distance is. That's root 3 times a, right? That would be root 3 times a. We figured that out last class. Here, we're not going that entire distance, though. We're going that distance divided by 4. We're only going a quarter of the way, okay, in this structure. And that distance needs to be equal to the radius of our cation plus the radius of our anion. Are there any questions on that derivation, on how we got to that? The only way that we could do that is by knowing that this was located at 1 quarter, 1 quarter, 1 quarter. I couldn't just show you a picture of that and expect you to know that. That, by definition, is the zinc blende structure. So things like that you would know, right? I wouldn't expect you to do that on a test. You'd have to know that that was located at 1 quarter, 1 quarter, 1 quarter, which is why we can do the body diagonal divided by 4. Emma?
Why is it RC plus RA?
Okay, so you start here. Let's call this the cation. You do 1 radius of the cation and 1 radius of the anion to get there. Okay? So let's see how close we get. When I plug these in, let's solve for A. It's going to be 0.6 plus 1.8, roughly. We're going to multiply that whole thing by 4. And we're going to divide it by the square root of 2. And I get that the lattice parameter should be something like 6.78. So let's see if that's even remotely close. Thank you. Square root of 3, thank you. Divide that by square root of 3. So it should be 5.54. Thank you, good catch. So lattice parameter, zinc blende. Let's do zinc sulfide. The lattice parameter is 5.41. And I calculated, even with like arbitrary, a little bit off radii values, 5.54, which is pretty flippin' close, right? So does this make sense how you do this? Let's do another example. Let's do a simpler one. Let's go back to sodium chloride. Tell me what the lattice parameter of sodium chloride should be. Work this out with your neighbor. I'll remind you that the size of sodium, the radius of sodium, and the radius of chlorine. Chlorine was 1 point. Let's double check it. Chlorine was 1.81. Sodium is, I think it's 1, is 1. So what should the lattice parameter be here? Okay, anybody got a guess for us? Experimentally, when they measure it, the lattice parameter is about 5.46 or 5.64. What do we get? Well, the lattice parameter should be equal to this entire lattice parameter. They touch along this side right there. It's going to be 2 cations and 2 anions. So 2R cation plus 2R anion. So when we plug those in, 2 times 1 plus 2 times 1.81 gives me 5.62, which is exactly what the value is, 5.64, right? So this is a pretty slick way to go between the size of these unit cells, the types of the unit cells, and just knowing basic things about the size of ions. The size of ions, you can look up in these tables. And they're pretty accurate. I mean, there's mistakes here and there's approximations, but this gets us pretty close. And using these tables, you can estimate what type of structure it is and how big is that structure with just some really simple applied geometry. Okay? Any questions? Yeah. Yeah. So again, on this one, they're touching along this side right there. And if it's ever not clear where they're touching, what I've got is I'm going to make all these, you're going to download Vesta for the homework this coming week, and I'll make all these things available. And you can always just click sort of space filling and say, oh yeah, sure enough, they touch along this edge length of the unit cell. They touch right along there. Okay? And that'll make it a little easier to see. So since they touch along that edge, there's 2 cation lengths and 2 anion lengths. Any questions? Yeah. A is what we call the lattice parameter. That's this length from there to there. It's the, because it's cubic, by definition, the sides in the X, Y, Z direction are all equal. There's other crystal systems that exist where that's not the case. We're going to get to those. I hope to get there today, but we're not going to get there. Okay, so that's the zinc blend structure. Okay? I'm going to skip that. How about this one? This is the first time where the coordination number is not equal. You've got the gray atom. What's its coordination number of the gray atom? It's 6. 1, 2, 3, 4, 5, 6. Equidistant, ideally. But this red one is not. It's only surrounded by 3. So a coordination of 6 and a coordination of 3. What that means is that since this is surrounded by half as many there must be twice as many of them. And sure enough, this is the formula for TiO2, rutile. The white paint, anywhere you see white paint, it's almost for sure this structure. It's this molecule. Because it's dirt, hence it's cheap as dirt, so they make paint out of it. And this structure, for the first time, we notice something different. If this is A, and that's A, this is B. B is longer. This is like a rectangle. Okay? It's no longer a cube. We've left the world of cubic structures and hexagonal close packed, and now we introduce the very first of a new type of structure, which is called tetragonal. It's got 2 sides of the same, which are not equal to this one, but everything is still 90 degrees. Okay? If it's not 90 degrees, it'd be a different type of structure. Okay? So this is tetragonal. If we did the RC over RA, we would find that the coordination number of the cation equals 6. You'll have to trust me for the sake of time. You can go back later if you want. Punch in titanium divided by oxygen. It would give you a coordination number of 6, which is why titanium is surrounded by 6 oxygens. But oxygen is only surrounded by half as many titaniums. Because in the formula unit, right here, there is half as many titaniums as there are oxygens. If oxygen was also 6 coordinate, then the formula would have to be TiO. But since it's TiO2, there must be half as many titaniums available to surround the oxygen. This make sense? Yeah. The easiest is to pull up the file. So TiO2, you'd pull this up, and you'd say, where are they touching? And it will create the bonds for you. The way that it does bonds is you basically have it search. You say, starting with titanium, look for oxygens up to some distance away, and it will find them. So if you put in a crazy number here, like 5, it's going to find all sorts of crazy things. You just want the nearest ones, though, right? So let's go back and put in a normal number like 3, and it will find just the ones within 3 angstroms. You can then select these bond distances, and it will tell you, in fact, that that bond distance is 1.98 angstroms long. So this software is powerful. That's why I'm teaching you how to use it. It's free. It's powerful. It tells you all these bond distances, and it shows you where they touch in this crystal structure. Okay? We're out of time, so we'll pick up here next time.